Hello, welcome back. So in this video, I want to talk about something called a polytropic process. Now, we've had other kinds of processes. Remember, a process takes you from state one to state two. It takes you from two different, it's a way of going from one thermodynamic state to another. You may add heat or squeeze a system or somehow alter it. But it requires some sort of interaction with the environment to drive the system away from equilibrium, from one equilibrium point to another one. Anyway, we've had different kinds of processes. So we've had an isobaric process. So that meant the number of bears in the universe doesn't change. No, it means the pressure is constant. Like think barometer. We had isochoric. Or I've also seen this called isometric. Same thing. And these both mean the volume is constant. We've had isothermal. These mean temperature is constant. We will have some others coming up. We'll have one, I'll go and tell you now, and then we'll go through it later. There'll be one called adiabatic. We haven't seen this one yet, but adiabatic. Turns out that's going to mean there's no heat during the process. Okay, that's okay. Don't worry if that. Just don't worry about that right now. Think of it as like a really well-insulated pipe or something like that. Adiabatic. And then what I want to describe in this video is a little different. So these processes are defined by holding something physical, something I can really interpret, and holding that thing constant. Or over here, saying the heat is zero. Those are good ones to be able to kind of physically understand. It turns out it's really convenient to define something called a polytropic process. Now, unless you're dealing with a gas, you probably, well, these are more of theoretical interest because they give us a set of model processes that we can use kind of to approximate real things. Real processes aren't necessarily polytropic, but we can use it as an approximation. And it's simple enough that we can still do math, okay? So I'll write the definition and then we'll kind of describe it. So the definition of a polytropic process is a process where you hold P times V to the N. This is any number, it has to be real, but it can be positive or negative. It doesn't matter. It doesn't have to be an integer. It's not moles. It's just any number. And it just is a constant. Okay. So that's a polytropic process. What does that mean? Well, let's assume N is greater than 0. Okay. So with that, you know what? I take it back. Let's not even, I'll label them all in one spot. So we make our PV diagram. Let's think about what that would mean. So this means in a PV diagram that I can rewrite that to say P is some constant over V to the N. All right. Well, if N is 1, it looks like a hyperbola. It's very similar to what we have for an ideal gas at constant temperature. But this, I'm not talking about an ideal gas here. This could be anything. It's really about the shape, not the material. Okay, so when n equals 1, it looks like something like this. Okay, this is n equals 1. When n equals -2, well, it'd be even more saggy. So n equals 2, n equals 3. They never cross the axis. They're supposed to asymptote. Sorry about that. If I say n equals 0, that actually means pressure is constant. And if I were to say n equals -1, then that would actually look like this. I'm going to change color so you can keep track of this. It's getting cluttered, but okay. N equals -1 would actually give you a line P is proportional to V. And then I could do n equals -2, and then it's going to look like a parabola. And, 3 and 4, -3, 4, whatever. And you get the idea that just by changing n, you can get all kinds of different curves. And so we can use this family of polytropic processes as just modeling devices for many things. I should have said this. I think I jumped the gun. N is called the Polytropic Index. Right? N is the Polytropic Process or Index. Okay. So there are a number of things you could do. You could be given an initial pressure, an initial volume, a final pressure, and an index, and you could try to figure it out what the final volume was. But there are all kinds of things you can do, and then you can calculate work for things like that. So I will post a video, an example, where I do some of that, and you'll have some practice on the homework too. All right, so polytropic process is just another type of process. It actually has probably less physical interpretation. It's more just a convenient set of curves we can draw in the space of pressures and volumes. I just want to also say this. The right-hand side is constant, and you can see, if you think about it, it doesn't even have sensible units. I mean, whatever n is, whatever the index is going to change the units on that constant. So if n was 1, it'd go like Pascal times a meter cubed. If n was 2, it'd be like Pascal times meter to the 6th. If I had n equals 10, it'd be Pascal times meter to the 30th. So the constant doesn't even have standard units. So I wouldn't even bother trying to think of this as a physical quantity. It's not related to any conserved charge or conserved property that in any sensible way. So it's just, really just think of this as a family of curves we can draw and for which we can do math. So we'll do an example in a later video where we do that. All right, thanks for watching. Catch you next time.